All right, so we're going to start with number 2 here. You've got this firefighter climbing the flight of stairs. Oh, just like you guys were doing like 2 days ago, right? During that mini lab on power. So, when you were climbing the stairs the other day, what force were you doing the work against? Anybody? Who asked for number 2? So I can focus in on helping you. So, are you listening now? No? Yes? No? So what force, the other day when you guys were walking the stairs, what force were you doing the work against? What force did you have to find out and write on your sheets? That was the force you were using to do the force, and that was opposing your... I'm going to have to grade those labs that are sitting on my desk. Anybody, what force, you use the normal force to do work to go up the stairs. What force are you working against? Gravity, which is also known as your weight, right? So the force, so that would have to be in your Y here. Oh, we're kind of having an off morning here, guys. That the work they do is by their normal force which is equal and opposite the weight. And then, so distance upwards creates work. So it's important to show in these Y's that you understand that the work is only created if there's a force and a distance in the same direction. All right? All right, so let's see. From our equation sheet on this one, all we really need is our relationship for work, which is the work equals the force and the distance that are parallel to each other. So it's really work equals F parallel delta D parallel. We know our force, we said, is equal and opposite to our weight. We know that our weight is mg from long ago. So the work is going to be that force, mg, and however far I go up the ladder. And I think I'm given all of that. Let's see. I'm given the mass. It's firefighters, so I only know of one planet that has firefighters, Earth. And it's 9 meters up. So really, it's just plugging it in. What was that? Oops. 75 kilograms on Earth, so that's 9.80 newtons per kilogram, and mine went up 9 meters. And that'll give me my work in joules. Well, actually, it'll give it to me in Newton meters, which is a joule, but we can answer it in Newton meters. Let's see what they wanted in. They wanted in joules. Good thing a Newton meter is a joule, so I'd have the exact same answer in joules. They're equivalent to each other. Alright, so I'll pause for a minute. Let me know if you need help individually on that one. Alright, so we're going to go on to number 4. In number 4, very similar to number 2, that we have this athlete, in this case, rather than a firefighter, moving a vertical distance. This time accomplished it in a certain amount of time. And they're asking for the power output. So one of the main things you want to show in your Y here is that you understand what power is, and that power is the rate work is done. So the rate that work is done, so how quickly that work can be accomplished. It's not really a great way to say it, because that then implies that you're looking for the time. People also tend to say the amount of work that we've done in a specific time. No, that's the amount of work. It's really, you have to zone in on this idea that it's the rate that the work is being done. And we're going to look just at the average, so we'll look at the total work, the total amount of time. Work-wise, I'm going to cheat a little bit here and say C number 2, because I don't feel like writing it all again. So, because it's really, the work side of this is exactly the same as what we just went through for number 2. So let's see, equation-wise, I need to remember that an object's weight is mg, that work is that force parallel, magnitude of the displacement parallel, and also that from my equation sheet, my new one is that I need to use this time is my power with my work and my time. Oops. So the amount of power that it takes is the amount of work over the amount of time. So I'm interested in the power. My work that's going to be done is going to be the force that the athlete needs to use to go up the rope, which would be equal and opposite to their weight, the distance they go up the rope, and the amount of time that they do it in. And now it's just plugging my values. They tell me my athlete has 74 kilograms, goes 5 meters up in 9 seconds. So I have a 74 kilogram athlete on the planet Earth. Newtons per kilogram goes up 5 meters in 9.0 seconds. And that will give me my power in watts. Some things just to make sure that you watch for. Always working your base units. I know some of you I can see from the side are working on like number 6. Make sure that you look at your distances in meters. So you end up with joules. If I didn't have newtons and meters up top here, I wouldn't end up with joules. If I don't have seconds down the bottom, I don't end up with watts, because a watt is a joule per second. So my suggestion as always is get into your base units at the beginning of the problem. Then you don't have to worry about, am I forgetting that I'm using a distance in centimeters or parsecs or something weird like that. If I'm always in meters, I know I'm going to come out to my base units. All right? So watch that on this problem, and not as much on this one, but on other ones. All right? I'll help you individually on it if you need it.